Tonight, I am super privileged to introduce our guest speaker, Dr. Borcu Kosar. Hopefully I pronounced that close to being correct. And Dr. Kosar works at NASA Goddard Space Flight Center, and she's going to tell us all about the Geospace Dynamics Constellation, which is a heliophysics program. So this is our big year of heliophysics. As you know, we had that eclipse in April, and the sun is going into solar max, so it's going crazy and all sorts of flares are happening. So it's an exciting year to be learning about heliophysics. And Dr. Kosar has a BS and MS and PhD in physics, all from Florida Tech. And she also does citizen science. I'm sure she can tell you more about the Spiritacular project. And she is the liaison for this mission she's going to tell us about. And hopefully she can also share a little bit of her personal things that she likes to do. So I like camping, but I don't hike, I ride my horse. It's a lot easier.
Well, that sounds good, Lynn.
Okay, so please take it away, and I'll try to answer any questions in the chat that I can, but we'll save all the really hard ones for you for later.
Okay, yeah, sounds good. Thank you so much for that kind introduction. Just to, I guess, add to that, I wear multiple hats at NASA Goddard. I study sprites and lightning. I am the GDC mission liaison, which is a mission to study the neutral atmosphere, pretty much the thermosphere, that I'll talk all about it shortly. But and I also love outdoors, camping, hiking. I'm actually going on a trip in April, which I'm super excited about. I also love doing like do-it-yourself kind of thing. I refurbish old furniture. I do a lot of house renovations. It's almost like I love giving life or second chance to old items. And I don't like them being like ending up like a landfill. So it's kind of something that I take pride in doing. But without further ado, I want to switch to my slides to introduce you guys to GDC mission, NASA's Next Living with a Star mission. I'll turn off my camera and I will start sharing, and please somebody let me know if you guys actually see my slides.
They're very tiny at the moment.
Okay, so what I'll do is, sorry, I will fit them, play from the start. And how is it now? Is it good?
Yeah, that's perfect.
Perfect. Okay, hi everybody. I think I gave my intro, but it's my pleasure to be here and introduce you guys NASA's Next Living with a Star mission called Geospace Dynamics Constellation. I'm the science team member working on developing multi-point analysis tools for this mission, as well as the mission liaison. I work with science activation teams, pretty much kind of educating the different types of audiences about what this mission is going to do and what its science is all about. So I'm representing the entire, about 100 people, GDC, pretty much entire science team, engineers, instrument developers, and project scientists and deputy project scientists. So thank you so much for this invitation. It's my pleasure to be here. So NASA's Heliophysics Division has these fleet of satellites that are probing different regions of the Sun-Earth system. As you guys can see, there's many different satellites in many different stages here. The color code is, for example, the yellow ones are still in formulation stage, orange is in implementation, greens are primary ops, and pretty much blues are extended missions. But this is pretty much the fleet that we have probing different regions. Some are Earth's magnetic field, some are near Earth space environments, some are actually studying sun and the solar wind. And as you guys can see, GDC mission, it's kind of represented as a single satellite here. However, in parentheses, you can see it will have 6 identical satellites that are going to be orbiting in low Earth orbit at about 400 kilometers that will be studying Earth's upper atmosphere. That is the primary purpose of GDC mission. And We are planned to launch early next decade, I would say around 2032, but we are doing all the mission work ahead of the time. That's why we belong to the formulation phase. And GDC is primarily going to probe the near Earth space environment, pretty much the region of the pretty much the upper atmosphere around our home planet. So I mentioned a couple of these, but as you guys can see in the image here, these are kind of planned orbits of these 6 satellites. It will create some kind of constellation architecture. It will fly in an altitude of 300 to 400 kilometers, which is the thermosphere of the thermospheric region. And this is also where the International Space Station flies. The mission primarily planned to be about 3 years, but with an extension of 2 years for an extended period, so total of about 5 years. So GDC mission is planned to answer some of the critical science questions about the Earth's upper atmosphere. So it's going to be focusing on understanding how Earth's upper atmosphere pretty much respond to variable forces externally and internally, meaning that some of these energy or some of these forces are coming from sun's connection to the Earth's magnetic field or direct solar radiation impact on the Earth's upper atmosphere, or atmospheric processes that are happening in the lower regions of the atmosphere and energy and momentum is being pushed into the upper atmosphere. It creates this very dynamic region called the upper thermosphere or upper atmosphere, where there is the mass energy and momentum is redistributed in a certain way. The dynamics is very complex. We'll get into the details of this a little bit later on, but GDC's purpose is to untangle these complex dynamics, to pretty much shed light in some of these processes, guide our physics and modeling and understanding of this area of the upper atmosphere. So let's start by taking a closer look at the Earth's atmosphere and maybe dive a little bit into what I mean by upper atmosphere. So Earth's atmosphere, as you might all know, primarily made up of nitrogen and oxygen, pretty much molecular nitrogen, molecular and atomic oxygen, and the density will be decreasing exponentially as you go up in the atmosphere. There are different ways to characterize the layers of the atmosphere, but the one that we are looking up here is kind of organized in terms of the temperature. So the lowest region, if you start from the ground up, as you go up towards the troposphere, you will see the temperature decrease and you will experience some temperature increase through the stratosphere. Mesosphere is the coldest region of the atmosphere, but then you will switch and have the atmosphere, the temperature going up, and now you are actually in the thermospheric region. And in each region, we have different atmospheric phenomena. All the weather as we know it happens in the troposphere. Usually airplane flights take place in the stratosphere. Mesosphere is home to some really exciting atmospheric phenomena, such as we see the meteor deposition to this altitude. Also, we see lightning's impact into the mesosphere, which generates electrical discharges, such as sprites and pretty much halos and elves, different kind of electrical discharges that are actually connected to the troposphere. In the thermosphere, usually this is pretty much the low Earth orbit altitude, where we have many of our technological assets fly, which are our satellites that are probing the Earth for different phenomena. They take different types of measurements. We also, in the thermospheric region, we see the northern lights or aurora. Beyond the thermosphere, it's pretty much outer space. So when I say thermosphere, when I talk about GDC mission and upper atmosphere, we are primarily referring to studying the thermospheric region. And this is where we have a special interest in understanding further, for multiple reasons. The first one is this is actually a transition region of pretty much composition and temperature. I'll talk about that a little bit more later on. In this region, the observations are very scarce, like we have very limited observations to actually understand the dynamics of this region. And also thermosphere is almost like a I would call it like a sandwich region in the atmosphere. There are forces coming from above and below, which creates this rich and complex dynamics in this region. So understanding the thermosphere is very important. So what's actually so special about this upper atmosphere or thermospheric region that we talk about? So the short answer is that the neutral atmosphere and the ionosphere, which is the ionosphere, which is in the form of a plasma, which has a lot of charged particles, they coexist in the thermosphere. So it's almost like thinking like thermosphere being embedded within the ionosphere. So above 600 kilometer in the atmosphere, in our atmosphere, ionospheric plasma or charged particles dominate. So the particles the charged particles in here, beyond the 600 kilometer, are actually connected to Earth's magnetic field. So they respond to electromagnetic forces. However, below 100 kilometer, actually the neutral atmosphere dominate. Neutral particles will move very different than electrons and ions. Actually, the charged particles, they will not respond to electromagnetic fields. Neutral winds, they don't respond primarily to electromagnetic fields, but they are primarily driven by the heating-induced pressure gradients, which can be caused by absorption of solar radiation, Joule heating, or particle precipitation in the upper high latitude ionosphere, or other frictional heating sources. Or neutrals can move as a result of a momentum transfer between ions and neutrals, or maybe because of inertial forces such as centrifugal or Coriolis forces. And another way that neutrals can move is the wave and tidal forcing from below. These are some of the sources that actually will let the neutral particles in motion. So in the thermosphere, energy sources from the sun, the solar wind, and the lower atmosphere combine together to create this very rich and complex behavior. So that's what actually makes the thermosphere very special and a special interest for the geospace dynamics constellation mission. So I talked about a lot of energy sources that are impacting the upper atmosphere. And I think it's good to look at some of these energy sources that provides input to the upper atmosphere. So the first one is the solar radiation. As you might know, sun emits electromagnetic energy in different wavelengths, all the way from radio to X-rays, pretty much visible, UV, infrared. They all have different wavelengths, and they are absorbed in different layers of the atmosphere. As you guys can see here, visible and infrared light can penetrate all the way to the ground, while most of the UV light, ultraviolet light, are absorbed in the thermosphere, and X-rays are also absorbed in mesosphere and thermosphere. So what does absorption do in the atmosphere? So when these ultraviolet UV radiation is absorbed, it transfers its energy to the atmospheric constituents, and it will cause them to actually heat up. And another way the solar radiation impacts the upper atmosphere, this UV and X-rays, because of their high energy, they actually play a very crucial role in ionizing Earth's upper atmosphere. They're pretty much primarily responsible for generating the ionosphere, which is the region where we have a very high concentration of charged particles. Pretty much it's in the state of plasma. So the another one is, as you guys might know, I want to talk about energy deposition coming all the way from sun down to the Earth's upper atmosphere. This is kind of a very large scale connection, so I try to stitch together with a bunch of videos that I'm going to start shortly. But as you guys might know, we are already, because of the heliophysics big year, you might be familiar that we are in the solar maximum period. So during solar maximum, sun has a very complicated magnetic field structure. So we have these active regions forming on the sun, and they are creating solar eruptions and very dynamic space environment. So as you might know, sun generally loses its mass in the form of solar wind, but during the very active times, we have something called solar eruptions. This can include solar flares, solar energetic particles, or CMEs, which is just this burst of mass into interplanetary space. We are usually protected by all of this by the Earth's magnetic field. However, if the conditions are right, this coronal mass ejection, this plasma that is ejected into the space, if it's aligned correctly, I'll play this video here one more time. As the coronal mass ejection comes and hits the Earth's magnetic field, if it's the right orientation, it will open it up. And in the night side, these magnetic field lines will reconnect and transferring these energy and particles into the upper atmosphere. And one of the best visual manifestation of this chain reaction event happening all the way from the sun to the upper atmosphere is actually the Northern Lights. This is the video of Northern Lights recorded from the International Space Station. And as you guys can see, aurora extends very high up in the atmosphere. It starts from 100 kilometers. It can go all the way up to 300 kilometers. There are different colors. They're both from atomic, they're coming, but this emission green and red is primarily from oxygen, but the energy of the particles that are causing these emissions are different. So primarily, upper atmosphere, in short, draws energy from these geomagnetic storms. Once the CME actually hits the magnetic field, transfer the energy in the upper atmosphere, particles precipitate, interact with the constituents of the upper atmosphere, and transfer some of their energy and cause them to get excited. And the re-emission of light is pretty much what we see in the form of aurora. So they also deposit electromagnetic energy in the high latitude. Aurora primarily forms in the north on the southern high latitudes of the Earth. So this electromagnetic energy deposition also cause heating of this upper atmosphere, and in the high latitudes it will cause neutrals to lift up, expand, and it's almost like as you deposit energy, it will heat up the atmosphere. Atmosphere will expand. If you guys can see this blue envelope around the Earth is kind of meant to describe what happens to the thermosphere when you deposit energy and heat it up. It will expand and contract. It's almost like the upper atmosphere is breathing. It's not just this stable layer of the atmosphere staying there doing nothing. It's actually very dynamic. So upper atmosphere not only impacted by forces coming from above, but it's also impacted by forces coming from below. Some of these are planetary waves that happen due to Earth's rotation, some tidal forces. Tides are actually happen because of the differential heating from the sun, meaning that sun is heating the day side and night side is cooler. So this differential heating will drive tides. Also gravitational pull on the atmosphere from the moon. Another lower atmospheric forcing into the upper atmosphere are the gravity waves. Gravity waves are generally generated by various sources on the ground. We can say the topography. When I talk about topography, it's very high mountains. When a storm system come over, it will be pushed up because of this, and it will induce some gravity waves propagating upward. Volcanic eruptions are another source, and actually thunderstorms, because of the updrafts and downdrafts inside them, they launch these concentrically expanding gravity waves into the upper atmosphere. So these planetary waves, tides and gravity waves are actually feeding energy into the different portions of the atmosphere. So they travel up, sometimes they break, and they deposit their energy and momentum, which is further complicating all these dynamical things happening in the upper atmosphere. So when we combine all of these energy sources, all the way from sun, from geomagnetic storm and the lower atmosphere, when they all combine in the upper atmosphere, it generates this highly dynamical system that you guys can see in this figure here. The processes that we are looking here they're all in multiple different spatial and temporal scales. So this is a very famous figure. I know this is very complicated, but we will unpack this a little bit. So let's say we take everything out and let's look at what happens when the solar radiation hits the Earth's upper atmosphere. We don't include the magnetic field lines here. So what sun does primarily by radiation is it establishes a baseline and it creates the ionosphere. So it ionizes the day side and pretty much it establishes the ionosphere. So even this simple process, I talked about differential heating, causing the neutrals to move, creating tides and the gravity waves coming from below, already creates a very dynamic environment in the upper atmosphere. So now if we into this system add Earth's magnetic field, pretty much what magnetic field does is it kind of separates the motion of ions and neutrals. So you got the ions or charged particles will be tied to the presence. I mean, pretty much if we have magnetic field, they will be tied to the magnetic field and they will kind of move with it. However, neutrals will not respond to any kind of electromagnetic fields. So they move differently. Ions move differently in the presence of magnetic fields. So this kind of separates, this separate motion of plasma and neutrals creates these pretty much disturbances and instabilities in the thermosphere. So now if we add the geomagnetic storms, which I try to describe that these coronal mass ejections coming from the sun, hitting the magnetosphere, and if they align correctly, transferring all that energy into upper atmosphere in the form of particle precipitation will heat up the upper atmosphere. So in the pretty much the high latitude region, the changing magnetic fields in here will be creating electric fields. Electric fields will set particles in motion, creating pretty much currents in the ionosphere. So all of these, they will impact the neutral atmosphere as well. So all of these changes happening in the high latitude, pretty much in the polar regions, they don't stay there. They actually propagate into the low latitude areas, creating this impact all around the globe. So I tried to show you guys a little simulation here that we did. This is one of the geomagnetic storms. So this is the neutral temperature in the thermosphere before a storm hits the high latitude. So when the storm hits from the high latitude and start depositing its energy, as you guys can see, neutrals do not just heat up there. So this whole impact propagates globally all around the Earth. So it's not kind of constrained in the high latitude only. So disturbances that are caused in the upper atmosphere result in a phenomena called space weather. So just like that we have weather on Earth, we have weather in space. It's a bit different, but it has a significant impact to society and technology. As you guys can see, there are many satellites that are currently orbiting around the Earth. This dense region that is very close to the Earth is Earth's low Earth orbit. That's where many of our satellites actually live. That's also where GDC is going to launch. And as I mentioned, when all of these energy sources hits Earth's upper atmosphere, it causes it to expand. So all of these satellites in their orbit, they're going around with a certain velocity to keep that orbit, and they have a certain drag on them. All of these are calculated when we launch these satellites to orbit. In the condition of a normal thermosphere, they just follow their orbital trajectory. However, when we have particle precipitation being deposited in the high latitude by a geomagnetic storm, it will cause the thermosphere to expand. So when the thermosphere expands, you will start feeling more drag on the satellite, and this drag will slow it down. And when it slows down, it will kind of change its orbit. And as you actually create pretty much the current flow in the ionosphere, it will heat it even more. So it will even expand the thermosphere further, which means more drag. And if this is not corrected, sometimes orbit operators need to correct the orbital parameters or kind of make corrections in the orbit to overcome this. But if we don't know, if we don't have measurements from this region of the upper atmosphere, we are kind of doing these corrections a little bit blindly and trying to do our best. So GDC's measurements will actually provide a very, very important feedback into these orbit operations, protecting our very important assets, our satellites that are going around the orbit, making very important measurements. So one example, I don't know, maybe you guys heard about this, but in February of 2022, Starlink lost about 40 satellites, and this was due to a minor geomagnetic storm. This wasn't even a major geomagnetic storm. Pretty much what happened is all of this energy deposition caused the thermosphere to expand, and it kind of caused about 40 satellites to deorbit, and they re-entered into the atmosphere, and that was kind of a big loss. So for Starlink, so this is pretty much the prediction or understanding of the thermosphere and how it responds to differential forcing from above and below is very important, especially to protect our assets in orbit. So another thing that I can talk about space weather is if the ionosphere is unperturbed. If you guys look at the video on the left here, for the state of the ionosphere that is unperturbed, the radio waves emit properly. But if you have a perturbed ionosphere as a result of a geomagnetic storm, you will actually see your signal degrading and you have communication problems. Another one that is supposed to loop, but I think it's stopped, but solar energetic particles or high energy particles, that they can actually impact the electronics of the satellites, and they can create, we can actually lose communication with the satellites if the impact is very large. So another thing space weather does is, because we have currents set in the ionosphere, they will induce currents in the ground. So if we have pretty much power lines or very long metal structures, these currents can run through this. And if these currents are strong enough, they can cause transformers exploding. So pretty much highly impacting our electrical grid. So the space weather has very important implications for society and technology, and understanding it will allow us to be better prepared for these events. So these are some of the simulation results for one of those geomagnetic storms that I talk about. We have in the very center, this is an ionospheric electron density simulation, and in the right side, the right three spheres are pretty much simulations of the neutrals, the neutral temperature and zonal and meridional winds. This is kind of showing response of energy input from the high latitude and how it actually redistributed around the globe. This doesn't even include impacts or forcing from the lower atmosphere, which will actually complicate this picture even further. This is our state of the understanding of the ionosphere thermosphere system currently. However, as I mentioned earlier, the data is very lacking from this area. So usually to be able to validate the predictions of these physics-based models or to constrain them, we actually need data. So GDC is exactly going to do that. It will obtain in situ data from this critical region, which will help us better our numerical models, better our understanding, and better our space weather prediction. So GDC is, as I mentioned, it will be a constellation mission in low Earth orbit. However, GDC is currently planned to be a phased mission, meaning that originally in phase 1, satellites will be close together when they launched into the orbit to make measurements in a local regime. The reason we wanted to do this is because we want to study the things that we want to study in the upper atmosphere. If you remember the earlier plot, they have different spatial scales, meaning that they have different sizes. So if you're always far away from each other, you're going to miss small scale things. Or if you're always close to each other, this time you'll be missing large scale processes. Because we want to tackle all these different types of scale sizes of events in the upper atmosphere, we designed a phase mission, meaning that we will have a local phase, which is satellites are very close to each other. Then we will have a regional phase. They will drift apart from each other, so they cover a larger area, and a global phase when they are kind of covering the entire globe, making measurements, things like planetary waves, which are very large scale waves going all around the planet, for example. That will be when GDC will be measuring in the global regime. So GDC currently is designed to have 6 instruments on board. So each satellite will have identical instrument suites. So current instruments that are selected are Ether, Nemesis, CAPE, Mosaic Profile, and TPS. And all of them will make measurements on the neutral atmosphere, energetic particles, pretty much ionospheric plasma, and they will make measurements of all electric and magnetic fields, pretty much giving us a wonderful data from this data start field of Earth's upper atmosphere to improve our understanding of how this system actually works. And it will inform us about space weather so we can protect our technological assets. So that's it. Thank you so much for listening. I think I have some time to take some questions. I will maybe stop sharing and turn on my camera to see if anybody has any questions.
Well, we have a good question in the chat that came from Sid. That's sort of because I pointed out that the gravity waves that you study are not the same as the gravitational waves that
Yes.
we detected with LIGO. So could you
Yes.
say a few words about what causes your kind of gravity waves?
Yes, so that's actually one of the most first misnomers. So gravitational waves, they happen in neutron star collisions out in space, and they propagate, create ripples in the space-time fabric, and we make measurements. That's a very different concept. Gravity waves or I would say atmospheric gravity waves are usually generated by perturbing a fluid. So if you have I would say like waves in imagine layers of the atmosphere as material, and you perturb it with something. Imagine the thunderstorms have this motion of updrafts and downdrafts, meaning that air mass moves up and down, and this kind of a source to generate gravity waves. It's kind of because of buoyancy forces. So when you perturb a certain location, it will launch this wave. It's in the form of an acoustic wave. Like if you compress a medium and if you just give it a push, it will kind of propagate in the form of a wave. So those are the atmospheric gravity waves that I'm talking about. There are a lot of different things that can set these gravity waves or launch them into the atmosphere. If a storm encounters a mountain and pushes up, that motion will set a gravity wave. Eruption of volcano will set a gravity wave because it will heat the certain region and it will generate gravity waves propagating upward. Like I said, updrafts and downdrafts, this circular convective motion in the thunderstorm will generate gravity waves. So they are caused by multiple different sources, but it is pretty much the buoyancy forces in the atmosphere. They are very different than the gravitational forces that happen out in the universe and space. So that's a great question.
Okay, so they're not really gravity waves, they're more like atmospheric material pushing up on, well, more atmospheric material that's higher in the atmosphere.
Yeah. That's pretty much it there. That's why we kind of, maybe it's a better way to say atmospheric gravity waves. Yes. But great question.
Yes, excellent. Okay, well, thank you very much. I think we're sort of out of time for questions. Ariana always does a little evaluation wrap up here at the end, but thank you so much for telling us about this exciting satellite, especially because we really need to keep track of space weather during
Yes.
solar maximum.
Yes,
And
definitely.
hopefully the government will continue to let us have that data.
Yes, we really hope so. We are hoping that we get to launch GDC, which is a very important mission for heliophysics.
Okay, well, thank you very
Thank
much.
you so much.